Hello, and welcome back to the course on quantum mechanics. We are still on the 6th chapter for this course. So before we proceed with this lesson, let us first review the previous lesson. So from the previous lesson, we have described a perturbed system wherein its new Hamiltonian H still obeys the eigenvalue equation. So psi n here are the new states, the perturbed states, and En here are the perturbed energies. And the Hamiltonian is basically just the original Hamiltonian plus the perturbation. Now, in our discussion for the previous lesson on first order non-degenerate perturbation theory, we'll let the new wave functions to be a power series in lambda, similarly with the energy. And what we did is we substitute psi n and En to our original eigenvalue equation, and for the first order theory we collect all of the terms containing lambda to the power of 1, the first order terms. Hence we get the first order theory. Now in this lesson we will be talking about the second order theory, wherein we will collect, after we substitute these two to this eigenvalue equation, we collect all of the terms containing the power of lambda squared so that we can go to the second order non-degenerate perturbation theory, and we can then get the second order corrections in the energy of the system. So collecting all of those terms, we have this. So we actually have 5 terms. And simplifying to solve for the second order correction and energy En2 or En squared, we get this equation. So psi L is a summation of L not equal to N, and you have the expectation value of the Hamiltonian of the perturbation, expectation value of the perturbation, then you get the absolute value squared. So again, absolute value squared means you conjugate the term, multiply with itself, and of course you have the difference in energies. So now if you are asked to find the energy of the perturbed system up to second order corrections, and then you will just need to add the zero order correction or the unperturbed energies plus the first order correction, and then this one, the second order correction. So take note that the first order correction energy is just the expectation value of the Hamiltonian or expectation value of the perturbation with respect to the unperturbed states. So let's go directly to an example. So we have this example in the previous lesson. You have a perturbed infinite square wave potential where there is a delta function at the center of the infinite square well. Now we already have obtained the first order correction in energy for this case. So you have a correction of 2 alpha over A for odd energy levels. So E1, E3, E5, E7, those have energy have first order corrections, but the odd energies have the even energy levels have 0 corrections or have no first order corrections. Okay, so for this case we need to solve for the second order correction meaning we need to use this equation. So if you are trying to solve for the second order correction in energy, it is advisable not to directly solve this equation because this is a summation. So first things first, we solve for the expectation value of the perturbation with respect to psi L0 and psi N0, the unperturbed states, where L is not equal to N. Take note. And then we next solve for the difference in energies, En0 minus El0. Now take note, this is an infinite square well potential, meaning your psi n's have the form square root of 2 over a sine n pi x over a, and your ENs, the energies, are n squared pi squared h bar squared over 2ma squared. Okay, let's first solve for the expectation value of the Hamiltonian. Sorry, the perturbation Hamiltonian. Okay. So we have, let's first solve for this one first. Psi L0 H prime psi m 0. Okay, so we need to convert this into the integral form. So psi L0 is square root of 2 over a sine L pi x over a, and psi n0 is square root of 2 over a sine n pi x over a. Our Hamiltonian, or sorry, our perturbation is alpha, then the Dirac delta function at x minus a over 2. So you will have a factor of 2 over a, and then times alpha, so 2 alpha over a, and then the integral of, here you will get sine L pi x over a, and then in the middle you have the Dirac delta function, your perturbation, which is just alpha times the Dirac delta function, x minus a over 2, and then for this one you have sine n pi x over a dx. This is from 0 to a. So again, you have a Dirac delta function inside your integrand, or in the integrand, meaning you don't need to integrate. So this is just basically 2 alpha over a sine, so at x is equal to a over 2, so you have sine L pi over 2 sine n pi over 2. Okay, so take note here that n is already at, that is the first condition. Okay, we then solve next for the difference in energies. This one, En0 minus El0. So En0 minus El0. So you will just get, this is n, so meaning you have n squared minus L squared, then pi squared h bar squared over 2m a squared. So you substitute this and this to our equation here. So you take the absolute value square of this. So since this doesn't contain any imaginary components, then it's basically just the square of this. So you square this one divided by this one, and you take the summation for L is not equal to n, and you will get I'm just gonna simplify, I will leave the exact details to you, but you will get something like this: 8m alpha squared over pi squared h bar squared summation of L not equal to n, and they must be odd. You have 1 minus n squared minus L squared. So that one. Take note that the values of sine here can be 1 or 0. Actually, can be depending on L and n. So if n and L are even, they're both 0. Or if either of one of them is even. But if both of them are odd, then you have basically 1. So meaning L and n must both be odd, because if either one of them, even if L is odd but n is even, or the reverse, if n is odd but L is even, then it will become 0. So both of them, L and n, must be odd. Now I will leave this as for you to exercise, for you to research. This is highly mathematical. This summation is actually equivalent to negative 1 over 4n squared. So negative 1 over 4n squared. That summation is equivalent to that one. So therefore, the second order correction in energy, if this is negative 1 over 4n squared, is just given by, this one. So if n is even, there's no second order correction. If n is odd, there is a second order correction, which is equivalent to this one, negative 2m alpha squared over pi squared h bar squared over n squared. Now, what does this mean? The first order correction and second order corrections only apply to odd energy levels, meaning E1, the ground state, will have, or sorry, in general, if you have an odd energy level, there will be a first order correction and second order correction. This is the first order, 2 alpha over a. This is the second order correction. But if you have even energy levels, then they don't have a first order correction, and they also don't have a second order correction. And basically, the perturbed even energy levels is just equal to the original unperturbed energy levels. Okay. Next example is for a harmonic oscillator potential. So find the energies up to second order correction of a particle trapped in this perturbed harmonic oscillator potential energy. So if you will recall, the potential energy, if a particle is trapped in a harmonic oscillator potential, is 1/2 kx squared. Now, there's a new potential energy, U prime. It's 1/2 k prime x squared, where k prime is 1 plus epsilon k. K is the original wave wave number or spring constant, depending what type of system it is. So this is the original k. This is the new k, k prime. And so basically you have k plus epsilon k, or you will get k prime minus k is equal to epsilon k. So that one. The original potential energy of an unperturbed harmonic particle trapped in a harmonic oscillator system is just 1/2 kx squared, and the original or unperturbed energies for a harmonic oscillator potential is n plus 1/2 h bar omega. Take note, omega and k are actually related. Omega is the angular frequency, k is the wave number. So omega is square root of k over m. Okay. So we first solved for the first order correction, because this is energy after second order correction. So we need to solve for the first order correction. So the perturbation, you sandwich it, or you take the average of that or expectation value of that with respect to the unperturbed states. But now, first things first, what is the perturbation of the system? So if you will recall, the new Hamiltonian of the system is the unperturbed Hamiltonian plus the perturbation. So therefore, the perturbation is just the new Hamiltonian minus the unperturbed Hamiltonian. So the new Hamiltonian is just kinetic energy plus the new potential energy, in this case it's U prime, minus the original or unperturbed Hamiltonian, assuming there's no changes in kinetic energy. So kinetic energy plus the old or the original unperturbed potential energy, U. So k will cancel out, the kinetic energy will cancel out, and then you will just have U prime minus U. U prime is 1/2 k prime x squared, U is 1/2 kx squared. So you will have 1/2 k prime minus kx squared. But k prime minus k is just epsilon times k. By the way, our assumption here is that epsilon is very small, such as it's a perturbation, a small disturbance, a small disturbance in the system. So you will have epsilon kx squared, but 1/2 kx squared is defined as U. Therefore, the Hamiltonian is epsilon times the original potential energy U. So EU, or 1/2 epsilon kx squared. So that is our Hamiltonian. Sorry. Now, to solve for the first order correction, so we need this formula. En1 is just psi n0 h prime psi n0, and h prime, where h prime is we will just use the, in terms of the potential energy, no? Epsilon times U. So in this case, you will have epsilon is just a constant. We can take it out of the expectation value, and you are left with epsilon expectation value of psi n 0. U psi n 0. And what is this one? When we discuss about the wave functions of a harmonic oscillator and its energies, we actually have this as an example, the expectation value of the potential energy. And the expectation value of the potential energy, so this term here is actually just the expectation value of the potential energy, and it's equal to 1/2 of the total energy, 1/2 En, or in this case En0, the unperturbed energies. We already have answered this before. So basically, this is just 1/2 epsilon En0. So this is the first order correction in energy. 1/2 epsilon En0, where En0 is n plus 1/2 h bar omega. So going back, this is now our first order correction. It's 1/2 epsilon En0, where En0 is the unperturbed energy, n plus 1/2 h bar omega. It's that one, easy peasy. You don't need to do some complicated calculations. Okay, let's now go to the second order correction in energy. So for the second order correction in energy, we need to use this equation. And again, as I have advised you earlier, you don't need to solve this directly. You first solve this expectation value of h prime, and then the energy difference in the denominator. So let's first start with this one, the expectation value of h prime. Okay, so I will have psi L0 h prime psi n0. So after I obtain this one, I'm gonna take the square of that, or the absolute value square of that. Okay, now unlike before, when we discuss about, and when we solved the first order correction in energy earlier, this doesn't have the same substrate. This is psi L and this is psi n, and they are not the same. L must not be equal to n. So we are forced to use the expanded version of this, which is just 1/2 epsilon kx squared. So we take out 1/2 epsilon k, we take it out of the expectation value, 1/2 epsilon k, and then you will have the expectation value of psi L0, and then x squared psi n0. So the expectation, this is basically the expectation value of x squared with respect to psi L0 and psi n0. Now, when we discuss about the harmonic oscillator, it's easier to deal with the harmonic oscillator system if you use the concept of ladder operators. So A plus and A minus. A plus is the raising operator, A minus is the lowering operator, and the position x can be represented as this constant square root of h bar over 2m omega, and the addition of the raising plus the lowering operator. So therefore, x squared is basically just this one. So h bar over 2m omega, square of a plus, a plus a plus, a plus a minus a plus, and a minus or a minus squared. Take note that a plus acting on the wave function will actually raise the wave function. So from psi n, it will raise it to psi n plus 1 with a constant of square root of n plus 1. And a minus acting on a wave function will lower the state or the wave function. So from psi n, it will lower it to psi n minus 1. Take note that we are using shorthand notation here for the wave function psi n. So psi n basically is just n, a very shorthand notation. So we have n, and that basically means psi n. So meaning this is psi m psi n. The inner product or the orthonormality condition of psi m psi n is delta m n. Now we use this x squared this x squared here, apply it. So you will just change this into shorthand notation. Just change this into L x squared n, so it will be easier. So use x squared, so this one, in terms of the raising and lowering operator acting on n, and then take the inner product with L. And when you do that, I'm just gonna leave that as an exercise to you. So you will get a value of 1/4 epsilon h bar omega, and then square root of n plus 1, n plus 2, delta L n plus 2, plus square root of n times n minus 1, delta L n minus 2. Okay, so this is now our expectation value of our perturbation. We then next solve for the difference in energy, En0 minus El0. So this is harmonic oscillator potential energy. So meaning this will just be n plus 1/2 minus L plus 1/2 h bar omega. So that one. So you can simplify that one to n minus L, n minus L. So basically it's n minus L h bar omega. Okay, so you substitute now this one, you put this in the denominator. Sorry. So you put En minus El0 in the denominator here. And this one, the expectation value of our perturbation, you take the absolute value. So there's no imaginary part here, so just take the square of this and put it in the numerator here. And then take the summation. Now, what is the square if your terms involve delta, Kronecker delta functions? So take note, this Kronecker delta function is 1 if L is equal to n plus 2, and it is 0 if L is not equal to n plus 2. And this one is only 1, the value of this Kronecker delta is 1 if L is equal to n minus 2, 0 if L is not equal to n minus 2. So if you take the square of that one, so the square of this one, the square of the delta function is just the delta function. It's just 1. The square of 1 is 1. And the square of this is also 1 because it's also the same. The square of the delta function is just itself because its value is either 1 or 0. The square of 1 or 0 is just 1 or 0. So the square of this is n times n minus 1. It's in the square, so the square of this is n plus 1, n plus 2. And then you have the cross terms. Now, if you have two delta functions side by side in a term, their value is 0 essentially. So for example, in this case, you will have a cross term. When you square this one, you will have cross terms involving delta L n plus 2 and delta L n minus 2. Now, if this delta function is 1, meaning L is equal to n plus 2, then this delta function is 0 because L is already n plus 2. So if you have two delta functions with different subscripts, then it's basically 0. So the cross terms, when you square this one, is just 0. So the square of this term is just the square of this plus the square of that. The cross terms are 0. Okay, so when you substitute that one, you will have something like this. Your second order correction in energy will now be equal to, I'm just gonna simplify, epsilon squared h bar omega over 16 summation of L not equal to n of n plus 1, n plus 2, the square of this term, delta L n plus 2, plus n minus 1, delta L n minus 2 over n minus L. That one. So this is now our equation. Now, if you will notice, there can only be two values or two terms in the sum. Only two terms in the summation of will survive because of this Kronecker delta function. So one value of L is n. L is equal to n plus 2. So when L is equal to n plus 2, this is equal to 1. This is equal to 0. And for the second term, that is when L is equal to n minus 2. So when L is equal to n minus 2, this is just equal to 1, but this is equal to 0. So only two terms in the summation will survive. And simplifying that one, only the two terms, L is equal to n plus 2 and L is equal to n minus 2. Take note, for any value of L that is not equal to n plus 2 and n minus 2, both of these Kronecker delta functions are 0. So basically, 0. And you will get this value for the second order correction. So it's negative n plus 1 half h bar omega epsilon squared over 8, or it's negative 1/8 epsilon squared en 0. So you will notice that the first order correction and the second order correction can be written in terms of the unperturbed energies en 0. So if you are trying to find the energy up to second order correction, then can factor out en 0. So the first order correction, zero order correction, unperturbed energy, en 0. Then the first order correction, 1/2 epsilon en 0. And the second order correction, negative 1/8 epsilon squared en 0. And you can actually go higher. And if you will notice, I don't know if you're familiar, this is actually a binomial expansion formula. So this is if you expand this up to the higher order terms, you basically get 1 plus e to the 1 plus epsilon to the 1/2. The binomial expansion of 1 plus epsilon to the 1/2, where epsilon assume is very, very small, very much smaller than 1. That one. So you can actually this is actually an exact solution or an exact energy of the perturbed system, not just up to second order correction, but this is the exact energy of the system. So you can actually not use perturbation theory in order to achieve these new energies of the perturbed system. So I will leave that as an assignment for you to research. Okay, for our last example, we have a charged particle in a harmonic oscillator potential, and it is in a weak electric potential energy, U prime. So find the energies up to second order correction for this system. So you have a particle in a harmonic oscillator potential that is the unperturbed system, but then we expose it to a weak electric field, and that weak electric field will have a corresponding additional potential energy, negative q e, force. Q is a force times x, the distance, force times distance. That's basically energy, work transformed into energy, U prime. So this is actually our perturbation now. Okay, so in order to get the first order correction, En1, we again sandwich our perturbation, which is just this one, the additional potential energy of the system, with respect to the original wave function. So in the case of the harmonic oscillator, instead of psi n, we'll just write this as n. So our first order correction, En1, will just be n, and then h prime n. So that's the shorthand notation. So h prime in this case is negative q times the energy electric field. By the way, so that will not be confused. This is, by the way, this is electric field. There's a subscript small e here to signify that this is not energy, because we're also using E for energy. So this is electric field. So you have negative Q times the magnitude of the electric field, and then you will have N X N. Okay. So this is just the expectation value of X in a harmonic oscillator, expectation value of the position of the particle in a harmonic oscillator potential. And this is actually equal to 0. We actually have proven this before. Because take note, for a harmonic oscillator potential, it's basically an oscillating, the value of X is actually oscillating. Half the time, the value of X is positive, half of the time, the value of X is negative. Therefore, the average is 0. So the average position is 0, the average momentum is also 0. So therefore, there is no first order correction for this system. So for the second order correction, we again go back to this equation. Again, we will solve this first, and then this one, and plug it back to this equation. So we first get this term here. So I'm just going to use shorthand notation, and so I'm just going to use L, and then H prime N. So I will have negative Q, the electric field, and then L X N. Okay, so now this is different from this, because this is this is just the expectation value N X N, but this is L X N. So in that case, we again need to use the ladder operator. So we let X be equal to this one. So you will have a factor square root of h bar over 2m omega, then a plus plus a minus, where again a plus acting on n, our wave function, will result in square root of n plus 1, n plus 1, so psi n plus 1, and a minus acting on our wave function psi n will get square root of n psi n minus 1. So when you do that, you will get this result. So I will leave that to you. So you have a factor of h bar over 2m omega, and then you will have square root of n plus 1, chronicle delta L n plus 1, plus square root of n, chronicle delta of L n minus 1. Again, this chronicle delta comes from the orthonormality condition. So for this delta, this actually comes from L and n plus 1, because the first X, the first term here is the raising operator a plus, so you have n plus 1, so you have L n plus 1. This is chronicle delta L and n plus 1. Similarly here, this is L and n minus 1, inner product of L and n minus 1. Okay, so that's it for the basically expectation value of h prime with respect to L and n, psi L and psi n. And then we will get the difference in energy, En0 minus El0. And again, this is just from our previous result, n minus L h bar omega. So again, we substitute this one, En minus El0 here, and this one here. Take the square of this. Again, the square of this is just the square of the first term plus the square of the second term. The cross terms again will be 0 because of the chronicle delta functions. Okay, so you square that one, divide by this, and then take the summation. And again, similar with the previous case, only 2 terms in the summation. So in this summation for En2 or En squared, only 2 terms will survive. L is equal to n plus 1 and L is equal to n minus 1 because of these chronicle delta functions. And you will get En2 be equal to negative q squared electric field magnitude squared over 2m omega squared. So that one. So therefore, if you are to approximate the energy of this perturbed system up to the second order correction, so you have the the zero order correction or the unperturbed energy. There is no first order correction, and it jumps directly to the second order correction, which is given by this value. That one. So that is it for a charged particle in harmonic oscillator potential energy and subjected to a weak electric field. Take note, this is weak electric field because, again, perturbations are assumed to be very small disturbance in the system. So that is it for this lesson. So in the next lesson, we will now consider a more general time-independent perturbation theory, and that is the degenerate perturbation theory. That is when there are now many states having the same energy, En. So in that case, we need to use the degenerate perturbation theory. And actually, the degenerate perturbation theory is actually a more generic theory, so you can actually use it for the non-degenerate case. So I will see you again in the next lesson.